The vast majority of the universe is unknown. We do not know how large it spans, or even if it is the only one, but much of what we do know about our galaxy and those immediately surrounding us is thanks to spectroscopy, the science concerned with the investigation and measurement of spectra produced when matter interacts with or emits electromagnetic radiation. Electromagnetic radiation refers to the waves of the electromagnetic field that carry electromagnetic radiant energy through space and time. The electromagnetic field is composed of the electromagnetic spectrum, possessing from low energy to high energy, radio, microwave, infrared, visible, ultraviolet, X-ray, and gamma-ray light waves. There are various forms of spectroscopy, the type being dependent upon the frequency of light being used. For the purpose of an example, we will look at the ultraviolet to visible light spectrums, and what happens when photons in these regions of the electromagnetic spectrum are absorbed or emitted by atoms. When an atom absorbs a photon, it absorbs its energy, exciting the atom's valence electrons up an energy level. In an excited state, the atom is more unstable and wants to move back down to its original energy state. So it does, and in the process emits a photon equal to the difference in the energy levels. The light emitted in this energy transition process is unique to each element, thus acting as a fingerprint for astronomers to use when identifying the elements composing celestial objects. Each element's unique emission spectrum is found through separating the different wavelengths of light emitted by the element with a prism through the process of refraction. Oftentimes, in lab experiments, the flame test is used to identify elements because when an element is burned, the color of light seen can be still used to estimate what is being burned. Although the flame test is not as accurate as looking at the electromagnetic spectrum through an electroscope, it can still be useful for school purposes. However, scientists attempting to discover what composes distant stars have to use far more precise instruments. In order to learn about these distant objects, astronomers have to conduct research in a controlled laboratory setting to collect data to be compared to that gathered from space. Astronomers use spectrometers to map each element's electromagnetic spectrum to determine its unique pattern. These unique patterns are the key to much of our knowledge of distant space. With what is called the Doppler effect, the electromagnetic pattern of any given element is shifted right or left along the electromagnetic spectrum, so that the wavelength of each line in the pattern becomes shorter or longer. This shifting of the element's electromagnetic spectrum is called a red or a blue shift due to its movement toward a lower or higher frequency light, and is dependent upon the movement of a star from which the element is coming relative to the position of the observer. From this shift, astronomers can deduce the radial velocity of an object and its movement towards or away from Earth. A blue shift indicates a movement towards Earth, while a red shift indicates a movement away from Earth. This is because by the time light is emitted from a moving object, the position of the object has changed, therefore compressing or stretching the gap between crests in a wavelength. As an object moves towards the viewpoint, the time between the release of a photon of an excited element seems to quicken, giving the appearance of a shrinking wavelength, causing a blue shift. While on the other hand, as an object moves away from a viewpoint, it seemingly takes photons longer to be released from an element, causing the appearance of a stretch in the wavelength and a red shift. At the point where the observer is parallel to the moving object, the wavelength is seen at exactly the frequency that it is produced. The presence of a red shift and a blue shift is actually used to help explain the theory of the Big Bang, as some stars are perpetually in an increasing redshift as they expand out into space away from Earth where they are being viewed. To help visualize this concept, imagine the sound of an ambulance as it moves towards and away from you. Like light, sound moves in waves, so the same Doppler effect applies. As an ambulance moves towards you, the sound becomes louder due to its increasing frequency. When it passes you, the sound is exactly as it is produced with its original frequency. And as it moves away from you, the sound becomes quieter, having a lower frequency relative to you, the observer. Now imagine this as a star approaches an observation telescope. The same shrinking wavelength principle applies, and we see a blue shift in the star's spectrum shift. Another force that can shift spectral lines and provide information to astronomers about stars is gravitational redshift. As a photon attempts to leave a strong gravitational field, it will lose some of its energy, resulting in it having a longer light wavelength. This information can be used to identify white dwarf stars, such as Sirius B, that is 61,000 times denser than the Sun. This information, taken from the Mount Wilson Observatory, shows that its gravitational field is 30 times stronger than the Sun, causing its emitted light to have a significantly greater redshift when compared to that of the Sun. Neutron stars, collapsed stars, have an even greater redshift, while black holes, in theory, have an infinite redshift such that no light has the energy to escape. The width of the spectral lines can reveal the strength of stellar wind, with wider spectral lines indicating stronger winds. In summation, spectral lines have revealed the elements, density, temperature, strength of magnetic field, and the strength of stellar wind. Also, if the spectral lines are shifting back and forth, it could reveal that the star is orbiting another star. With the presence of another star, the masses of the two bodies can be determined with the information provided through the spectral imaging. With this knowledge, astronomers have identified more than 500 planets and stars orbiting other stars, as well as the many central stars themselves. Currently, NASA has employed mapping technologies in space, in near space, and on Earth to record data about stars, planets, and the Earth. Some of these include the Fermi telescope for gamma rays, the Hubble telescope for visible light, the Spitzer telescope for infrared light, and the Planck telescope for microwaves. With each day, these pieces of technology, and more, are expanding our knowledge of space. Thanks to spectroscopy, we now know more about the distant worlds than ever before.